The cosmos is not a serene painting of fixed lights. It is a living, breathing arena of chaos and wonder. Tonight, we are not looking at the familiar, steady stars. We are hunting for the rule breakers, the cosmic anomalies that behave in ways science cannot yet fully explain. By the end of this journey, you will know the 25 most enigmatic stars in our galaxy, each with a story that defies prediction. We will witness stars that dim for reasons unknown, stars that explode over and over, and stars made of elements that should not exist. What does the most unpredictable star in the sky make you wonder about our universe? Our journey begins with a star that is not just unpredictable but violently unstable. Eta Carinae is a monster, a hypergiant star located about 7,500 light-years away. It is not one, but likely two colossal stars locked in a deadly dance. What makes Eta Carinae legendary is its history of erratic, almost suicidal outbursts. In the 1840s, it underwent what astronomers call the Great Eruption. For over a decade, this star became the second brightest object in the entire night sky, outshining every star except Sirius. It was a cosmic tantrum of unimaginable scale. The star did not explode, but it violently shed an enormous amount of its own mass, blasting it into space at incredible speeds. That expelled material did not just drift away. It formed a vast, beautiful, and eerie structure known as the Homunculus Nebula, a twin-lobed cloud of gas and dust that still expands outward today, a permanent monument to that single event. Inside that nebula, the star itself remains hidden, seething, and unstable. Astronomers watch it constantly because Eta Carinae is a prime candidate for a supernova. It is a ticking time bomb on a cosmic scale. When it finally does go supernova, and it will, the event will be spectacular. From our safe distance, it would become as bright as the full moon, visible even in broad daylight for weeks. While its radiation poses no direct threat to life on Earth, it would be a brilliant, humbling reminder of the raw power contained within these enigmatic stars. Eta Carinae teaches us that sometimes the most unpredictable behavior is not a quiet mystery, but a roaring prelude to destruction. That explosive history is only part of the story. The true source of Eta Carinae's chaos lies in its very structure. It is not a single, lonely giant. It is a binary system, a pair of stars locked in a claustrophobic 5.5-year orbit. The primary star is an unstable behemoth, but its smaller, hotter companion is no less significant. Their dance is not a graceful waltz, but a violent, destructive grapple. Every 5.5 years, when the stars reach their closest approach, called periastron, the system erupts. The fierce stellar wind from the smaller, hotter star slams into the bloated, volatile atmosphere of its larger partner. This collision is not silent. It creates shock waves that heat the gas to millions of degrees, causing the entire system to brighten dramatically in X-rays, a scream of high-energy light that telescopes can detect across the galaxy. These regular, predictable outbursts are layered on top of the star's general instability, a rhythmic heartbeat of violence within the larger threat of a final explosion. The stellar winds from both stars are constantly at war, carving into the Homunculus Nebula and shaping it into those bizarre, billowing lobes. Think of it like two fire hoses blasting into a cloud of smoke, sculpting it into ever-changing, chaotic forms. This relentless interaction strips material from the stars, feeding the nebula and ensuring that Eta Carinae's surroundings are never calm, never settled. The binary nature of this star turns its unpredictability from a random event into a scheduled cataclysm, a clockwork of destruction that reminds us even the most chaotic systems can hide a terrible, beautiful order. The clockwork violence of a binary system is one kind of chaos. An entirely different mystery unfolded much closer to home, in the familiar shoulder of the constellation Orion. Betelgeuse, the brilliant red supergiant marking Orion's shoulder, is a star we all know. For centuries it shone with a steady, ruddy glow. Then, in late 2019, it began to fade. This was not a subtle shift. By February 2020, Betelgeuse had lost nearly two-thirds of its visible light. Astronomers and stargazers around the world watched in awe and concern. Was this the prelude to the supernova event of a lifetime? The great dimming of Betelgeuse became a global astronomical event, a puzzle broadcast across 640 light-years of space. The leading theory is surprisingly mundane yet fascinating. Betelgeuse is a massive, bubbling cauldron of a star. It constantly belches out vast clouds of gas and dust from its turbulent surface. Scientists now believe a particularly large, cool patch developed on the star's southern hemisphere. This cool spot allowed gas to condense into solid dust particles right there in the star's outer atmosphere. A colossal plume of this freshly formed stardust then drifted out, partially blocking our view of the star's surface and causing the dramatic dimming we witnessed. It was a cosmic sneeze on a monumental scale. By April 2020, the dust had cleared and Betelgeuse returned to its normal brightness, but the event served as a powerful reminder. This star is living on borrowed time. Betelgeuse is a ticking bomb, its core fusing elements at a frantic pace. It will explode as a supernova, and it could happen tomorrow or in 100,000 years. In cosmic terms, that is essentially any moment. When it does, the explosion will be a daytime star, visible for weeks and outshining the moon at night for months. It will be a harmless but breathtaking spectacle, a front-row seat to the death of a stellar giant and the birth of a new nebula. Betelgeuse teaches us that unpredictability is not always about hidden companions or violent outbursts. Sometimes it is a quiet, dusty veil drawn across an aging star's face, a fleeting glimpse of the profound changes brewing within. Betelgeuse showed us a star dimming behind its own dust. But what if a star dimmed in a pattern so strange it defied every natural explanation we could think of? This is the story of Tabby's star, officially known as KIC 8462852. Located over 1,000 light-years away in the constellation Cygnus, this ordinary-looking star became the most mysterious object in the galaxy thanks to data from the Kepler Space Telescope. Kepler's mission was to find planets by watching for the tiny, regular dips in starlight caused when a planet passes in front of its sun. But Tabby's star did not behave like a planet host. Its light did not dip by a gentle 1%. It plunged by enormous, irregular amounts, sometimes over 20%, and the dips lasted for days or weeks with no predictable rhythm. It was as if giant, jagged shapes of unknown origin were drifting in front of the star, blocking its light in a chaotic, unnatural dance. The strangeness was so profound that one astronomer, Jason Wright, famously suggested we had to consider an extraordinary possibility. Could these be signatures of alien megastructures like a Dyson sphere under construction? This hypothesis, while a long shot, captured the public imagination and ignited a firestorm of scientific and popular interest. It framed a fundamental question: were we seeing the handiwork of intelligence or merely a natural phenomenon we had never witnessed before? The hunt for an answer transformed this star from a data anomaly into a global citizen science project, with thousands of people poring over light curves and donating telescope time to keep constant watch. This public engagement proved crucial because the star kept surprising us. In 2017, it dimmed dramatically again, and astronomers around the world swung their instruments toward it, capturing its light across every wavelength they could. The data revealed a critical clue. The star dimmed more in blue light than in red light. That is a telltale sign of dust, not solid objects. Solid megastructures would block all colors of light equally. Dust, however, scatters blue light more easily, letting more red light pass through. This pointed toward a more natural, though still bizarre, explanation. The leading theory now involves a massive, uneven swarm of cold comets or the dusty debris from a shattered planet orbiting the star in a vast, clumpy cloud. Perhaps a catastrophic collision in the star's system created a chaotic ring of fragments that occasionally align to block our view. Tabby's star remains an enigma, but its legacy is profound. It showed us the power of public curiosity in science, and it taught astronomers a humbling lesson. Sometimes the universe invents mysteries we are not yet clever enough to immediately solve, and the most exciting answer is not always aliens, but a new, undiscovered chapter in astrophysics. Tabby's star challenged us with strange shadows, but Przybylski's star presents a mystery of pure substance. Located over 350 light-years away, this star looks ordinary at a glance, but its light holds a secret that has baffled scientists for decades. When astronomers analyze its spectrum, the chemical fingerprint of its atmosphere, they find elements that have no business being there. We are not talking about common metals like iron or nickel. Przybylski's star contains detectable amounts of promethium and einsteinium. These are short-lived radioactive elements. Promethium, for instance, has no stable isotopes. Its longest-lived form decays in just a little over 17 years. Einsteinium is even more fleeting, a synthetic element created in nuclear reactors and atomic tests. They are not elements found in nature on Earth, and they should not be lingering in the atmosphere of an ancient star. It is as if you walked into a medieval castle and found a smartphone charging on the stone table. The presence of these elements defies our understanding of stellar chemistry and nuclear physics. So where did they come from? One leading theory is as dramatic as it sounds. The star might be polluted, not by industrial waste, but by the debris from a dead companion. The idea is that Przybylski's star could be in a binary system with an invisible neutron star, the ultra-dense corpse of a supernova. This neutron star could be emitting a fierce wind of exotic particles, literally spraying these rare, radioactive elements onto the surface of its neighbor. It would be a form of cosmic contamination on a stellar scale. Another, even more profound theory looks inward, not outward. Perhaps we are witnessing unknown nuclear processes happening deep within the star itself. The intense pressures and temperatures in its core might be forging these bizarre elements through pathways science has not yet mapped. This would mean our models of how stars create and mix elements are incomplete, that there are entire chapters of nuclear alchemy we have not yet read. Przybylski's star is a quiet, unassuming point of light that whispers a revolutionary idea. It suggests that the periodic table we know might be written in starlight in ways we do not yet comprehend, and that the universe is still capable of cooking up substances that, by all our current rules, should not exist at all. The presence of impossible elements is a quiet chemical mystery, but some stars announce their unpredictability with a theatrical flare, vanishing before our eyes without warning. This brings us to the enigmatic variable star Eta Carinae borealis. Nestled in the small, semicircular constellation Corona Borealis, this star is the prototype of its own rare class, and its behavior is utterly bizarre. For months or even years, Eta Carinae borealis shines steadily at a brightness easily seen through binoculars. Then, without any signal, it plunges into darkness. Its light can fade by a factor of hundreds or even thousands over just a few weeks, becoming invisible to all but the largest telescopes. After languishing in this dim state for months, it just as abruptly returns to its normal brightness as if nothing happened. For centuries, these dramatic fades were a complete puzzle. What colossal object could periodically block so much starlight? The answer is not a planet or a swarm of comets, but something far more elemental: soot. Eta Carinae borealis is a carbon-rich star, a cosmic chimney of sorts. Astronomers believe that periodically, vast clouds of pure carbon dust condense right in the star's upper atmosphere. Think of a candle suddenly producing a huge puff of black smoke. This cloud of microscopic carbon particles, not unlike soot from a fire, billows out and forms an opaque shroud around the entire star. From our vantage point, the star seems to blink out. Eventually, the intense radiation pressure from the star itself pushes the dust cloud away, clearing our view and allowing the star to reappear. The trigger for these soot eruptions remains unknown, making each new fade an unpredictable event. It is a star that literally dims its own light with the elemental building blocks of life, a self-eclipsing giant playing a cosmic game of hide and seek. If our Carinae Borealis is a star that hides in its own soot, then V838 Canis Majoris is a star that is violently tearing itself apart in plain sight. Located in the constellation Canis Major, V838 Canis Majoris is not just large, it is a behemoth of almost incomprehensible scale. If placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, swallowing the inner planets whole. This is a hypergiant, a star in its final, unstable act. And it is not going quietly. V838 Canis Majoris is racked by titanic eruptions, ejecting massive amounts of its own material into space in sporadic, chaotic outbursts. These are not the gentle puffs of carbon dust we see with our Carinae Borealis. These are seismic stellar events, hurling gas and dust with the force of multiple supernovas spread out over time. The result is a spectacular, complex nebula that surrounds the star, a tangled web of filaments and arcs that astronomers have mapped in detail. This nebula is not a remnant from an ancient explosion. It is the star's own atmosphere being violently shed in real time. Each knot and plume in that nebula tells the story of a past eruption, a time when the star convulsed and lost another piece of itself. This ongoing, explosive mass loss is the clearest possible sign that V838 Canis Majoris is dying. It is in a runaway phase, desperately unstable as it fuses the last fuels in its core. The star's incredible size and furious activity mean its end is inevitable and, in cosmic terms, imminent. It will almost certainly end its life in a spectacular supernova, or perhaps even a hypernova, leaving behind a black hole. Watching V838 Canis Majoris is like watching a building collapse in slow motion, with each eruption another piece of the structure falling away, a prelude to the final, catastrophic demolition. Even the most trusted guide in our night sky holds a secret pulse. Polaris, the North Star, is the celestial landmark by which explorers have navigated for millennia, a fixed point of light in the turning heavens. But this constancy is an illusion. Polaris is not a steady beacon. It is a Cepheids variable star, a type of star that rhythmically swells and shrinks, growing brighter and dimmer over a regular cycle. For Polaris, that cycle takes just under 4 days. This pulsation is a delicate balance act deep within the star, where layers of helium alternately trap and release radiation, causing the entire star to breathe in and out like a colossal, luminous lung. The change in brightness is subtle to our eyes, but measurable, proving that even our most reliable marker is throbbing with hidden life. More intriguing is that this pulse is not constant. Over the last century, astronomers have watched the period of Polaris's pulsation change. It is gradually lengthening, slowing down. This means the internal engine driving this stellar heartbeat is itself evolving, a sign that Polaris is undergoing a fundamental transition in its later life. We are witnessing, in real time, a star changing its own rhythm, and the plot thickens further when we look closer. Polaris is not alone. It is the brilliant primary member of a complex triple-star system. The star we see is Polaris A, a supergiant. Orbiting it is a much smaller companion, Polaris B, visible through a modest telescope. But there is a third, even closer companion, Polaris AB, detected only through precise measurements, locked in a tight dance with the primary. This gravitational ballet between 3 stars introduces subtle tugs and influences that complicate the simple picture of a solitary pulsating giant. The presence of these companions may affect the star's mass loss, its rotation, and ultimately the stability of its pulsations. All of this leads to a profound uncertainty about the future. Polaris's role as our North Star is temporary, a consequence of the slow wobble of Earth's axis called precession. In about 12,000 years, the bright star Vega will claim the title. But the more immediate question is what will happen to Polaris itself. As its pulsations slow and it interacts with its hidden companions, will its behavior become more erratic? Could its gentle pulse one day cease or become wildly unpredictable? The star that has symbolized certainty for human civilization is, in truth, a changing, dynamic system whose long-term fate is written in equations we are still learning to solve. Our steadfast guide is on a journey of its own, and we are just beginning to read the map. Pulsations like those of Polaris are a gentle heartbeat, but some stars breathe with the force of a cosmic gale. Meet Mera, officially Omicron Ceti, a star that does not just vary, it transforms. For most of its 332-day cycle, Mera is a faint, reddish pinprick, invisible to the naked eye. Then, over the course of months, it awakens. It swells and brightens not by a modest percentage, but by a staggering factor of 1,000, becoming one of the brightest stars in its constellation before fading back into obscurity. This incredible cycle earned it its name, Mera, meaning the wonderful or the astonishing, and for good reason. It is the prototype of an entire class of stars known as long-period variables, the elderly, unstable red giants whose outer layers pulse with this slow, dramatic rhythm. The cause is a delicate and unstable fusion process in a shell around the star's core, causing the entire outer atmosphere to expand and contract like a colossal dying bellows. But Mera's wonder does not end with its brilliant pulse. In 2007, observations from a space telescope revealed something astonishing. Mera is not merely pulsating in place, it is racing through space at an incredible speed, over 290,000 miles per hour. As it charges through the thin gas between stars, it leaves a spectacular trail in its wake, a glowing, comet-like tail of material it has ejected over its long lifetime. This tail is not short. It stretches over 13 light-years in length, a stream of stellar matter that would take light itself over 13 years to travel from one end to the other. To picture that, if our solar system were a marble, Mera's tail would be a ribbon longer than the distance to our nearest stellar neighbor. This tail is a fossil record of the star's mass loss, a visible timeline of its slow death by evaporation. Every pulse, every expansion hurls more of its substance into this cosmic slipstream. So when we look at Mera, we are not just seeing a variable star. We are witnessing a celestial comet, a runaway giant bleeding its atmosphere into the void as it journeys forever forward. Its brilliant, periodic flares acting as a lighthouse in the vast, dark sea of interstellar space. It is a reminder that in the cosmos, even the most predictable cycles are part of a grander, unstoppable motion. Mera's long tail is a gentle bleed into the void, but some stars are not content with mere evaporation. They feed. At the heart of the constellation, Aquila lies a system that takes stellar violence to an entirely new level. SS433 is not just an unpredictable star, it is a cosmic predator, a microquasar that demonstrates the most extreme physics in our galactic backyard. The system is a binary, a pair locked in a death spiral. A normal, sun-like star orbits an invisible monster, either a black hole or a neutron star. This is not a peaceful dance. The immense gravity of the dense corpse relentlessly strips material from its living companion. This stolen gas does not simply vanish. It forms a superheated, spinning disk of doom around the black hole or neutron star, a whirlpool of plasma called an accretion disk. Temperatures in this disk soar to millions of degrees, glowing fiercely in X-rays. But the real spectacle happens at the disk's poles. From there, the system fires out twin beams or jets of material at speeds so incredible they approach a significant fraction of the speed of light. These are relativistic jets, and they are not steady streams, they wobble. The entire accretion disk acts like a spinning top that is slowly tipping over, a process called precession. It completes one full wobble every 162 days. As these ultra-fast jets process through space, they point toward us and then away from us in a regular, dizzying cycle. This motion creates one of the most clear-cut and bizarre observations in all of astronomy. When a jet is pointed nearly at us, the light from its material is blue-shifted, squeezed to shorter wavelengths because it is moving toward us at a fantastic speed. When it swings away, the light is redshifted, stretched as the material races away. We see both a blue jet and a red jet from the same system, switching dominance as the top spins. It is a real-time demonstration of Einstein's theory of relativity painted across the spectrum. The energy involved is staggering, emitting intense radiation from radio waves to gamma rays. SS433 is a scaled-down version of the supermassive black holes that power distant quasars, but it is happening right here in our own galaxy, giving us a front-row seat to the mechanics of cosmic cannibalism and the birth of light-speed fountains that shape the space around them. These relativistic jets are a spectacle of directional violence, but what if an entire star system was sculpting its own beautiful and potentially deadly farewell? That brings us to WR104, a star that is both an artist and a potential assassin. Located about 8,000 light-years away, WR104 is a Wolf-Rayet star, the exposed, blistering hot core of a star that has already blown away its outer hydrogen layers. It is a stellar corpse in the making, shining with a fierce blue-white light as it fuses heavy elements in a last, desperate blaze of glory, but it is not alone. It orbits a massive companion star, and their interaction creates one of the most stunning structures in the cosmos, a perfect spiral nebula like a cosmic pinwheel etched in glowing dust. This spiral is not a static sculpture, it is a dynamic creation formed by the titanic collision of the two stars' supersonic stellar winds. As they orbit, these winds slam together, compressing and heating gas and dust, which then glows in infrared light. The result is a breathtaking, rotating spiral that traces their orbital motion with geometric precision. Yet, within this beauty lies a profound threat. Wolf-Rayet stars like WR104 are the prime candidates for producing the most powerful explosions in the universe since the Big Bang, long-duration gamma-ray bursts. These are not typical supernova. A gamma-ray burst is a focused beam of pure, lethal energy, born when such a star collapses directly into a black hole. The beam is so concentrated it can outshine an entire galaxy for a brief moment, but only if you are in its narrow line of fire, and here is the unsettling part. For years, astronomers debated whether the axis of rotation of WR104, and therefore the direction of any potential gamma-ray burst beam, might be pointed roughly toward Earth. If it were, and if the star exploded tomorrow, that beam of high-energy radiation traveling at the speed of light could deliver a significant dose of radiation to our upper atmosphere. It would not sterilize the planet, but it could damage the ozone layer, potentially triggering a minor extinction event by altering our climate and exposing life to increased ultraviolet radiation from the sun. Recent studies suggest we are likely safe, that the pinwheel is tilted enough to miss us, but the very possibility forces us to confront a sobering truth. A celestial object of stunning beauty, 8,000 light-years away, could hold the power to subtly, yet permanently, alter the course of life on our world. It is a reminder that the cosmos is indifferent, capable of creating art and apocalypse with the same set of forces. If WR104 represents a potential threat from a distance, our next star delivered a startling wake-up call from much closer to home. In April 2020, a dead star in our own galactic neighborhood did something unprecedented. SGR1935 plus 2154, a magnetar located about 30,000 light-years away, suddenly screamed. A magnetar is a type of neutron star, the collapsed core of a giant star, but with a magnetic field so intense it defies comprehension. If you brought a magnetar halfway to the moon, its magnetic field would erase the data from every credit card on Earth. This particular magnetar had been known to emit occasional bursts of X-rays and gamma rays, but on that day it did something more. It emitted a brilliant millisecond-long flash of radio waves so powerful it was detected by telescopes across our planet. This was a fast radio burst, or FRB. For over a decade, astronomers had detected these mysterious, incredibly energetic radio flashes, but they always came from other galaxies, billions of light-years away. Their source was one of astronomy's greatest puzzles. SGR1935 plus 2154 changed everything. For the first time, an FRB was detected originating within our own Milky Way, and it came from a known object, a magnetar. This event was the smoking gun, providing the first direct evidence that at least some fast radio bursts are generated by these unimaginably magnetic stellar corpses. The leading theory is that a starquake on the magnetar's rigid crust, strained by its own immense magnetic field, caused a catastrophic rupture. This rupture likely triggered a massive reconnection of magnetic field lines, an explosion of magnetic energy that accelerated particles to near light speed, producing that intense, fleeting blast of radio waves we observed. In a single millisecond, this magnetar confirmed a hypothesis and demystified a cosmic phenomenon, proving that the most enigmatic signals can sometimes come from the most extreme objects right next door. It showed us that our galaxy is not a quiet backwater, but a stage where stellar zombies can still unleash cries powerful enough to be heard across interstellar space. Magnetars scream their existence in bursts of raw energy, but some stars communicate through echoes of light. V838 Monocerotis is a star that told its story not with what it ejected, but with what it illuminated. In January 2002, this previously faint and unremarkable star, located about 20,000 light-years away, did something extraordinary. It suddenly flared, becoming 600,000 times brighter than our Sun in a matter of days. For a brief period, it was the brightest star in our entire Milky Way galaxy. This was not a typical nova or supernova. It was an eruption of unknown origin, a stellar event so peculiar it defied immediate classification. The true wonder, however, unfolded in the months and years that followed, as seen through the watchful eye of the Hubble Space Telescope. The star itself faded almost as quickly as it had brightened, but its legacy was just beginning to unfold. Surrounding V838 Monocerotis were vast, ancient shells of dust and gas it had shed in earlier, quieter phases of its life. These shells were dark and invisible to us, like layers of soot hanging in interstellar space. The brilliant flash of 2002 acted like a cosmic camera flash, firing a pulse of light into the darkness. That light traveled outward at, well, the speed of light. As it reached each successive dust shell, it lit them up from within. Because the shells were at different distances from the star, the light took longer to reach the farther ones. What Hubble captured was not an expanding blast wave of material, but an expanding wave of illumination. A sphere of light growing year by year, lighting up one intricate dust structure after another. It was a three-dimensional fossil record made visible, a time lapse of the star's own past. Each glowing ring represented a chapter in the star's history, a time when it had puffed away part of its atmosphere. The event created one of the most breathtaking sequences in astronomical history, a celestial bloom that appeared to grow faster than light itself, though it was only an illusion of geometry. To this day, the exact cause of the initial eruption remains a subject of debate. Was it a stellar merger, a planet being consumed, or a new type of thermonuclear event on a dying star? We still do not know for certain. V838 Monocerotis reminds us that sometimes the most revealing act is not an explosion, but a flashbulb moment that exposes the hidden architecture of a star's life, turning its history into a temporary, glowing sculpture in the void. The echoes of light from V838 Monocerotis reveal a star's past, but some stellar corpses spin so fast they warp the fabric of the present. PSRJ 1748-2446 AD is a pulsar, a city-sized ball of pure neutron star material, and it holds a dizzying record. It is the fastest spinning pulsar we have ever discovered, rotating over 700 times every single second. To grasp that speed, picture this. If this pulsar were the size of a grapefruit, its surface at the equator would be moving at roughly 1/4 the speed of light. A single rotation takes just 1.4 milliseconds. In the time it takes you to blink, this cosmic top would have spun over 400 times. Such a velocity should, by all classical logic, tear the star apart, flinging its material into space. So why does it hold together? The answer is a force of almost unimaginable density. A neutron star is what remains after a massive star's core collapses. The protons and electrons are crushed together into neutrons, creating matter so compact that a single teaspoonful would weigh as much as a mountain. This incredible density generates a gravitational field 100 billion times stronger than Earth's. It is this titanic gravity, this sheer weight of itself, that holds the pulsar together against the centrifugal force trying to rip it to pieces. It is a perpetual tug of war between spin and gravity, with gravity winning but just barely. The star is likely flattened at its poles, bulging at its equator, stretched into the shape of an oblate spheroid by its own furious rotation. This extreme spin does more than just create a dizzying spectacle. According to Einstein's theory of general relativity, any accelerating mass should ripple the fabric of space-time, creating gravitational waves. A perfectly smooth, spherical star would not produce them, but a rapidly spinning, slightly deformed one absolutely does. PSRJ 1748-2446 AD should be a steady, shrieking siren of gravitational waves, humming a constant note into the cosmos as its immense mass whips around. While these particular waves are too faint for our current detectors like LIGO to pick up individually, their existence is a powerful prediction of our physics. This pulsar is a natural laboratory for the most extreme conditions in the universe, a place where matter is stretched to its absolute limit and space itself is continuously stirred by its motion. It is a reminder that in the aftermath of stellar death, the most violent acts can give birth to objects of breathtaking precision, cosmic gyroscopes spinning in the dark with a stability that defies their own impossible speed. This dizzying spin is a testament to the neutron star's incredible resilience, but what if one of these ultra-dense cores did not spin alone in the void? What if it was swallowed whole by another star? Our 14th star, HV2112, might be exactly that, a cosmic cannibal caught in the act. This star in the small Magellanic Cloud is the leading candidate for one of the most bizarre theoretical objects ever conceived, the Thorne-Zitkow object. Named for the physicists Kip Thorne and Anna Zitkow who proposed it, this is not a binary system. It is a stellar hybrid, a Russian nesting doll written in fire and gravity. The model suggests a neutron star, the corpse of a supernova, could be captured by and spiral into the heart of a massive red supergiant. Instead of being consumed, the neutron star survives, orbiting within the star's vast, tenuous envelope like a planet orbits a sun, but buried deep inside the furnace itself. This creates a star within a star, a two-layered engine of unimaginable power. The red supergiant provides the hydrogen-rich outer layers, while the neutron star at its core acts as an immensely hot and dense furnace, processing material in ways a normal stellar core never could. For decades, this was pure theory, a fascinating thought experiment with no observational proof. Then astronomers looked closely at HV2112. Its light revealed a chemical fingerprint that was profoundly strange. The atmosphere of this red supergiant is overflowing with unusual elements like rubidium, lithium, and molybdenum. These are not the typical products of a red giant's fusion processes. In a standard star, lithium is quickly destroyed in the hot interior. Rubidium and molybdenum are produced in specific, rare nuclear reactions that require conditions far more extreme than a red giant's core usually provides. The neutron star core of a Thorne-Zitkow object, however, would create the perfect, brutal environment. As hydrogen from the giant's envelope rains down onto the neutron star's surface, it would undergo rapid proton capture processes, a frantic nuclear alchemy that could churn out exactly the exotic cocktail of elements we see. It is as if we found a factory designed to make steel instead quietly producing rare gemstones. The output tells us the machinery inside must be fundamentally different. While the evidence is compelling, the case is not yet closed. Some astronomers propose alternative explanations, like a rare type of super-AGB star. Yet, HV2112 remains our best, most tantalizing clue that one of the universe's most outlandish theoretical creatures might actually be real, a hidden monster burning at the heart of a giant, its presence betrayed only by the unusual chemistry of its host's glowing atmosphere. While HV2112 suggests a star hiding a monstrous core, other young stars wear their chaos on the outside, cloaked in vast spinning disks of primordial material. Among these stellar infants, a few stand out for behavior so erratic it redefined what we thought possible. These are the Dipper stars, a class named for their distinctive, sharp dips in brightness that resemble a child's drawing of a mountain range. The most famous of them all is EPIC 204278916, a young, low-mass star in the Scorpius constellation. In 2015, data from the Kepler Space Telescope's K2 mission revealed something astonishing. Over a 78-day observing period, this star's light did something unpredictable and extreme. It dimmed not by a gentle percent or two, but by a staggering 65%, and it did so in a series of sharp, irregular, and deeply asymmetric drops. The light curve looked less like a planet's transit and more like the shadow of a jagged, torn structure tumbling chaotically through space. This was not a single, clean event. The dips varied wildly in depth, duration, and shape, with some showing a steep ingress and a slow recovery, while others did the opposite. It was a signature of pure, unbridled chaos orbiting a very young star. So what could possibly cast such a bizarre, changing shadow? The leading hypothesis points to the star's youth. EPIC 204278916 is only about 5 million years old, a mere infant compared to our Sun's 4.6 billion years. At this age, it is almost certainly surrounded by a protoplanetary disk, a vast, flat ring of gas and dust where planets are beginning to coalesce. But this disk is not a smooth, featureless plate. The incredible dips suggest it is a dynamic, messy construction zone. Astronomers theorize we might be seeing the shadows of colossal, transient structures within that disk. Imagine a disk that is not flat but warped like a vinyl record left too close to a heater. A giant warp, perhaps caused by the gravitational tug of an unseen forming planet or a stellar companion, could periodically swing into our line of sight, blocking the star's light in an uneven way. Alternatively, the disk could be filled with immense, dense clumps of dust and debris, the raw materials of planets still coming together. These clumps would have irregular shapes and orbits, casting those jagged, asymmetric shadows as they pass. There is even a more dramatic possibility. We could be witnessing the aftermath of a catastrophic collision within the disk, where two protoplanets slammed together, creating a vast, expanding cloud of shattered debris that now drifts in front of the star, its shape evolving daily. EPIC 204278916 is not alone. It belongs to a growing family of similar young stars, often found in star-forming regions like the Taurus and Upper Scorpius clouds, all showing these strange dipper light curves. Each one is a unique puzzle, its specific pattern of shadows hinting at the different types of turmoil possible in a young planetary system. Studying them is like watching time-lapse footage of our own solar system's violent infancy, a phase when the orbits were not yet settled and the sky was filled with the dark, moving shapes of worlds being born. These stars tell us that unpredictability is not always a sign of decay or death. Sometimes it is the signature of creation itself, the messy, glorious, and shadow-filled process of building new worlds from stardust. The chaotic birth of planets is a shadow play of light and dust, but in a mature system, the dance can turn predatory. Cygnus X1, one of the most famous objects in the sky, is a name that evokes a singular image, a black hole. Yet the true story of its violence is written not in the invisible singularity, but in the tortured light of its companion, a brilliant blue supergiant star known as HDE 226868. This star is the visible half of a high-mass X-ray binary, a partnership defined by theft on a cosmic scale. Every 5.6 days, the two objects complete a tight, frantic orbit. The black hole, with gravity so strong not even light can escape, exerts a monstrous pull on its stellar neighbor. It does not just orbit the supergiant, it actively devours it, stripping away its outer layers of hydrogen and helium in a relentless stream. This stolen gas does not fall directly into the abyss. Instead, it spirals inward, forming a superheated accretion disk that swirls around the black hole at nearly the speed of light. Temperatures in this disk reach millions of degrees, causing it to glow not in visible light, but in an intense scream of X-rays, the very emission that gives Cygnus X1 its name and first alerted astronomers to its presence decades ago. The companion star, HDE 226868, is far more than a passive victim. Its very shape tells the tale of this gravitational assault. The star is not a perfect sphere. It is tidally distorted, stretched by the black hole's pull into a teardrop shape, with one side permanently bulging toward its invisible partner. This distortion affects the star's rotation and its own stellar winds, creating a chaotic and lopsided flow of material directly into the black hole's waiting grasp. We can even see the star's pain in its spectrum. As it whips around in its orbit, one side of the star is perpetually moving toward us while the other side moves away, causing its light to be Doppler shifted in a rhythmic, telltale pattern that reveals its orbital speed and the immense mass of the object pulling it along. This binary is a feedback loop of violence. The black hole's gravity shapes the star, and the star's stolen material feeds the black hole's fury, powering the X-ray furnace that makes the entire system visible across the galaxy. Studying Cygnus X1 is not just about observing a black hole. It is about witnessing the real-time consequences of one of the universe's most extreme relationships, where a brilliant giant is slowly, inexorably being consumed, its light forever marked by the shadow beside it. The predatory dance of Cygnus X1 reveals a star being slowly consumed, but another partnership in the cosmos creates not just destruction but art on a grand scale. R Aquarii, a star in the constellation Aquarius, is a living canvas where two stellar destinies intertwine in a beautiful, volatile symbiosis. To the naked eye, it is a faint, variable point of light. Through a telescope, however, it unveils one of the most intricate and dynamic structures in our galaxy. This is not a single star, but a deeply connected pair, a red giant and a white dwarf locked in a gravitational embrace that has lasted for centuries. The red giant is a vast, cool, and aging star, slowly puffing away its outer layers into space. Its companion, the white dwarf, is the exposed, Earth-sized core of a dead star, incredibly dense and hot. This is where the relationship turns from coexistence to a delicate, dangerous exchange. The red giant's gentle stellar wind carries a stream of hydrogen-rich gas across the void. The white dwarf's immense gravity captures this material, pulling it onto its own scorching surface. There, the stolen hydrogen accumulates layer by layer under incredible pressure and heat. For decades, this process seems stable, a quiet theft, but it is a slow-motion bomb in the making. Eventually, the accumulated hydrogen on the white dwarf's surface reaches a critical threshold. It ignites in a runaway thermonuclear explosion, a nova. Not a supernova that destroys the star, but a colossal surface blast that can increase the system's brightness 10,000-fold in a matter of days. Our Aquarii has experienced these eruptions multiple times in recorded history, with major outbursts noted in the late 19th century and again in the early 20th. Each explosion blasts a shell of newly forged material into space, but it does not destroy the white dwarf. The cycle simply resets, and the slow theft of hydrogen begins anew. The most breathtaking result of this cycle is not the blast itself, but its aftermath. The white dwarf, likely due to its rapid rotation and magnetic fields, channels some of this expelled material into two narrow, opposing beams, a bipolar jet. This jet, traveling at hundreds of thousands of miles per hour, plows into the older, slower-moving debris from the red giant, sculpting it into a spectacular, evolving nebula. Hubble Space Telescope images reveal a twisted, clumpy, S-shaped structure stretching over a light-year across. And here is the truly remarkable part. Because the nebula is only about 1,000 light-years away, we are close enough to see it change. Observations over just a few years show distinct motions in the knots and filaments of the jet. What we are seeing is real-time feedback from those periodic explosions, a cosmic sculpture being carved before our eyes over a human lifetime. Our Aquarii is a clockwork of creation and destruction, where one star's death throes provide the fuel for another's periodic rage, and together they paint a masterpiece that is never quite finished. The intricate symbiosis of our Aquarii is a delicate dance, but some stars reject such subtlety entirely. They are the cosmic titans known as luminous blue variables, a rare and violently unstable class of massive stars living on the very edge of existence. These are not just unpredictable stars, they are stellar catastrophes in slow motion, defined by their willingness to violently shed their own identities in sporadic, colossal outbursts. To understand them, look to the pioneers of this chaotic class. P Cygni, discovered in the 17th century, suddenly appeared as a new star in the constellation Cygnus, shining brightly for years before fading from naked eye view. It was one of the first recorded instances of a star announcing its instability with a brilliant, unexpected eruption. Centuries later, we recognize P Cygni as a prototype, a star that undergoes occasional giant eruptions where it expels vast shells of material, each outburst leaving a permanent mark in its spectrum and its surrounding nebula. Another magnificent example is Eta Carinae, a star strikingly similar to the monstrous Eta Carinae but slightly closer and easier to study. It is surrounded by a spectacular 3-light-year-wide nebula, a glowing testament to a past giant eruption that likely occurred over 10,000 years ago. This nebula is not a remnant from a final death, but a fossil of a temper tantrum, a time when the star blasted away a significant fraction of its own mass. The star itself continues to vary erratically in brightness, as if still shuddering from that ancient event. The behavior of these luminous blue variables places them in a precarious and fleeting position on the stellar family tree, the Hertzsprung-Russell diagram. They occupy a narrow, unstable region between the brilliant blue supergiants and the even more evolved Wolf-Rayet stars, which have already blown away their outer hydrogen layers. An LBV is essentially a supergiant in transition, a massive star that has become so luminous that its own radiation pressure threatens to blow it apart. The outward force of its intense light battles against the inward pull of its gravity, creating a state of perpetual, unstable balance. This balance is so delicate that it occasionally tips into chaos, resulting in those characteristic giant eruptions. During these events, the star does not explode, but it experiences a sustained, super-powerful stellar wind, ejecting solar masses worth of material over a period of months or years. It is a star literally tearing its own skin off in great, heaving sheets of gas. This extreme mass loss is the star's method of evolution, a violent shedding of its outer self to reveal the hotter, denser core beneath. For the most massive luminous blue variables, this is the final act before they transform into Wolf-Rayet stars and ultimately core collapse supernova. They are the universe's most dramatic transformers, using eruptions of unimaginable scale to change their own fundamental nature, reminding us that even for stars, growth can be a violently unpredictable process. Luminous blue variables transform themselves through violent eruptions, but the corpses of such stars can hide even stranger secrets. Our 20th star is not a star at all in the traditional sense. It is a cooling corpse, and its behavior is rewriting the rules of physics for the dead. Known by the catalog number CXOUJ1714005.7-381031, this neutron star is located about 13,000 light-years away in the constellation Scorpius. Neutron stars are the ultra-dense remnants of supernova explosions, city-sized balls of matter so compressed that a single sugar cube of their material would weigh as much as all of humanity. They are born screaming hot with temperatures exceeding 1 million degrees, and then they slowly cool over millions of years as they radiate their immense heat away into space. This cooling process is a cornerstone of astrophysical models, a predictable timeline of fading embers, but this particular neutron star is not following the script. Observations from space telescopes have revealed it is cooling down at a rate that is nothing short of shocking. It is losing heat far, far faster than any standard model of neutron star physics can explain. It is as if you pulled a red-hot iron out of a forge and watched it turn ice cold in minutes instead of hours. The discrepancy is so large it points to a fundamental gap in our understanding. So what could possibly be siphoning heat away from this stellar corpse with such efficiency? The leading hypothesis ventures into the realm of the truly exotic. Deep within the unimaginable pressure at the core of this neutron star, matter may not exist as neutrons at all. The neutrons themselves, under such extreme conditions, might be breaking down into their constituent parts. We could be seeing evidence of a quark-gluon plasma, a primordial soup of the universe's most fundamental particles, swirling in a superfluid state at the star's heart. This quark matter would conduct and radiate heat with phenomenal efficiency, acting like a cosmic heat sink and explaining the rapid cooling we observe. Alternatively, the core might be undergoing a continuous process of rapid neutrino emission. Neutrinos are ghostly particles that barely interact with normal matter, but in this environment, they could be produced in vast numbers and stream directly out of the star, carrying its thermal energy away into the void at nearly the speed of light. Either scenario forces physicists to confront the limits of their knowledge. The behavior of CXOUJ1714005.7-381031 is a direct probe into states of matter that cannot be created in any laboratory on Earth. It is a natural experiment operating at pressures and densities so extreme that the very rules of nuclear physics are bent. By watching this single point of cold light fade quicker than it should, we are essentially reading the internal diary of a dead star, a diary written in a language of quarks and neutrinos we are only beginning to translate. Its core is a laboratory for exotic physics, but our next star is a cosmic paradox built from the ashes of a double death. HD 144941 is an extreme helium star, a stellar oddity so rare we have only found a handful in our entire galaxy. At first glance, its composition seems to defy the basic rules of stellar life. Stars are born from clouds of hydrogen, and they spend the vast majority of their lives fusing that hydrogen into helium in their cores. Hydrogen is the fundamental fuel of the universe, yet the atmosphere of HD 144941 contains almost no hydrogen at all. It is a star made almost entirely of helium with traces of carbon and oxygen. It is like finding a car engine that runs not on gasoline but on the soot left behind after the gasoline has already burned. How could such a star exist? The leading theory is as dramatic as it is elegant. HD 144941 is likely the product of a stellar merger, the final act in the story of two dead stars. Picture a close binary system where both stars have already lived their lives and faded into white dwarfs. These are Earth-sized embers, the dense cores left behind after Sun-like stars shed their outer layers. One white dwarf is rich in helium, the other rich in carbon and oxygen. Over eons, they spiral closer and closer due to the emission of gravitational waves, the ripples in space-time predicted by Einstein. Eventually, they cross a point of no return and collide. The merger is not a destructive explosion, but a creative one. The violent union reignites nuclear fusion in the combined core, but not the hydrogen fusion of a normal star. This new, reborn star fuses helium, burning the primary fuel that was donated by one of its progenitors. The resulting object is a bloated, hot star that appears on the outside exactly as we see HD 144941, a helium giant with a hydrogen-depleted surface. This origin story places it on a unique evolutionary pathway, a road not taken by single stars. It is a stellar phoenix born from the ashes of two separate deaths. Its existence proves that the universe can recycle its dead into entirely new, bizarre forms of life. Studying stars like HD 144941 helps astronomers map the strange byways of stellar evolution, showing that sometimes the most predictable end, a white dwarf cooling into darkness, can be spectacularly undone by the gravitational dance of a companion. A stellar phoenix born from a merger is a cosmic rebirth, but other stars are not reborn. They are violently exiled. Zeta Ophiuchi is a stellar fugitive, a brilliant blue giant racing through the galaxy at nearly 66,000 miles per hour. This is no leisurely journey through empty space. Zeta Ophiuchi is plowing headfirst into a dense, slow-moving cloud of interstellar gas and dust. The result is a spectacle of pure force. Just as a speedboat creates a V-shaped wave in water, this star's immense stellar wind, a constant stream of charged particles, slams into the interstellar medium. The collision compresses and heats the gas, sculpting it into a vast, glowing arc that wraps around the star in its direction of motion. This is a bow shock, a brilliant wall of light that astronomers can see in infrared. The structure is colossal, stretching across several light-years, a permanent, fiery wake marking the star's reckless path. But what could launch such a massive star on this high-speed journey? The leading suspect is a past companion. Zeta Ophiuchi was likely once part of a binary system. Its partner, an even more massive star, lived fast and died young, exploding as a supernova. The sudden, asymmetric detonation would have acted like a cosmic cannon, violently ejecting the surviving star and sending it careening across the galaxy like a stone from a slingshot. Zeta Ophiuchi now travels alone, its brilliant bow shock a testament to the explosive event that set it free. Another runaway tells a different story of stellar ejection, one written not by an explosion but by a gravitational duel. Aorighi, the flaming star, burns with a fierce blue light in the constellation Auriga. By tracing its path backward through space, astronomers made a startling discovery. Its trajectory points directly back to the Orion Nebula, a stellar nursery over 1,500 light-years away. The math suggests that about 2.5 million years ago, Aorighi was violently flung from that region. The mechanism, however, was likely not a supernova. Instead, the best model involves a close gravitational encounter within a dense star cluster. Picture two tight binary star systems passing dangerously close to one another. The complex gravitational interplay during such a flyby can act like a slingshot, ripping one star loose from its original system and catapulting it into the void at tremendous speed. This is precisely what is believed to have happened to Eta Carinae. It was a stellar billiard shot on a galactic scale. Its furious motion now causes it to illuminate the surrounding gas cloud IC405, not with a neat bow shock, but with a more chaotic, flickering glow that gives it its fiery nickname. These two runaways, Zeta Ophiuchi and Eta Carinae, show us that the galaxy is a dynamic and often violent neighborhood. Stars are not fixed landmarks. They can be shot out of their birthplaces by the death of a companion or the gravitational machinations of their siblings, becoming lone wanderers that paint the interstellar medium with the brilliant signatures of their flight. Some stellar runaways are born from violence, but others meet their end in a different kind of fiery embrace. The story of V838 Scorpii is a tale of cosmic hindsight, a violent event we witnessed only because we happened to look back in time. In September 2008, amateur astronomers in Japan spotted a new star blazing in the constellation Scorpius. It was a nova, a sudden brightening, but this one was peculiar. It did not behave like a typical classical nova from a white dwarf. It brightened more slowly, peaked at a lower luminosity, and faded with a strange, reddish hue. Intrigued, professional astronomers scrambled to study it, but the real discovery came when they dug through archived images of that patch of sky from years before the explosion. What they found was extraordinary. The star had been there all along, quietly hiding in plain sight. It was not a single star, but a contact binary. Two sun-like stars so close together they were literally touching, sharing a common atmosphere of gas. They orbited each other in a frantic, decaying dance, completing a revolution in just over one Earth day. The archival data revealed this dance was speeding up. Year after year, the orbital period was getting shorter. This was the smoking gun. The two stars were not just close, they were spiraling inward, destined to merge. The gravitational energy released as they drew closer was transferred into their outer layers, causing the system to grow steadily brighter in the years leading up to the cataclysm. Then, in 2008, the inward spiral reached its inevitable conclusion. The stars finally plunged into one another, their cores merging. The resulting shockwaves blasted the shared envelope of gas into space in a spectacular eruption known as a red nova. This is not a supernova that destroys a star, nor a classical nova on a white dwarf. A red nova is the specific, luminous signature of two stars becoming one. The outburst of V838 Scorpii provided the first complete observational record of this entire process, from the slow, pre-merger brightening to the final, explosive union. It was like finding a security camera that had been recording a building for years. And only after the building collapsed did we think to check the tape, discovering the slow structural cracks that predicted the fall all along. This event gave astronomers a precious template, a light curve, and a set of chemical signatures that now help them identify other red nova across the galaxy. V838 Scorpii is gone, consumed in its own merger, but in its death it left behind a perfect blueprint for stellar rebirth, proving that sometimes the most dramatic explosions are not endings but violent, messy beginnings. The violent merger of two stars is a blueprint for a new beginning, but the final star on our list is a blueprint for something else entirely, a stellar death that defies every rule in the book. Its official name is a string of letters and numbers, IPTF14HLS, but astronomers simply call it the zombie star. In September 2014, automated telescopes caught a supernova in a galaxy 500 million light-years away. It was bright, it was dramatic, and it behaved exactly as expected for a Type II supernova, the explosive death of a massive star. For about 100 days, it faded steadily as all such supernovae do. The story should have ended there with a fading ember and a new nebula, but this star refused to die. After its initial decline, IPTF14 HLS did the unthinkable. It brightened again, not just once, but 5 distinct times over the next 600 days, pulsating with energy like a heart refusing to stop beating. Each brightening was like a mini explosion layered on top of the first. A series of violent hiccups that released more energy than our Sun will emit in its entire 10 billion-year lifetime. This was not a mere irregularity. It was a sustained rebellion against the fundamental physics of stellar death. A normal supernova is a single, catastrophic event where a star's core collapses and its outer layers are blasted into space in one tremendous, irreversible detonation. The zombie star suggested a core that collapsed, then somehow found the strength to explode again and again and again. For over a year and a half, it lingered in a state of perpetual eruption, outshining its entire host galaxy with its stubborn, undying light. The leading theory to explain this impossible behavior is as staggering as the observations themselves. Astronomers believe IPTF14 HLS may have been a pulsational pair instability supernova, a type of event thought to have occurred only in the universe's first generations of stars, monsters over 100 times the mass of our Sun. In such a behemoth, the core becomes so hot that light itself begins to spontaneously create matter and antimatter electron-positron pairs. This process steals the radiation pressure that was holding the star up, causing the core to become violently unstable. Instead of one final collapse, the star experiences a series of massive pulsations. It convulses, ejecting enormous shells of material in successive eruptions that can last for years, before the core finally runs out of fuel and collapses into a black hole. Finding such an event in the modern universe was like stumbling upon a living dinosaur. It implied that stars can still grow to these mythical, unstable sizes, and that their deaths can play out on timescales we never thought to look for. The zombie star is more than an anomaly. It is a relic. Its persistent, flickering light is a message from a bygone era of cosmic giants, a demonstration that the most extreme laws of physics are not confined to the distant past, but are alive, unpredictable, and shining in the darkness of the present. That stubborn, flickering light from a galaxy 500 million light-years away did more than just defy a single theory. The zombie star, IPTF14 HLS, forced a fundamental rewrite of the stellar death manual. For decades, astronomers had a clear, if dramatic, picture of how a massive star ends its life. The core runs out of fuel, gravity wins, and the star collapses in on itself before rebounding in a single, catastrophic explosion that scatters its guts across space. The light from that event rises, peaks, and fades over months. It is a one-act play. The zombie star revealed a production with multiple encores, a drawn-out tragedy where the curtain refused to fall. This meant our models were incomplete, perhaps missing a whole category of stellar demise that plays out over years, not months. It challenged the very timeline of destruction, suggesting that in the most extreme cases, death is not an instant but a protracted and violent process. This leads directly to a profound question about limits. The leading explanation, pulsational pair instability, requires a star of almost mythical proportions, 150 to 250 times the mass of our Sun. Until recently, we thought such monsters only existed in the early universe, made from the pure hydrogen and helium of the cosmic dawn. Their deaths were thought to be events of the distant past. The zombie star's appearance in a relatively modern galaxy tells us these behemoths can still form today. It pushes the boundary of what we believe is possible for stellar birth and growth in the current cosmic era. What conditions in its host galaxy allowed a star to swell to such an unstable size? Its existence hints at pockets of the universe where the ancient rules still apply, where stars can reach masses we considered impossible for contemporary times. The implications ripple outward into our search for understanding. If the zombie star is not a singular freak event, but a representative of a rare class, then our surveys have likely been misinterpreting the cosmic ledger. A typical supernova survey might observe a patch of sky for a few months, catch the bright peak of an explosion, and then move on. If a star then brightens again a year later, that event would be catalogued as a new supernova in that same location, not recognized as the stubborn continuation of the old one. The zombie star's true nature was only revealed because astronomers had the archival data and the persistence to watch its location for years after the initial blast. This means there could be more of these events hiding in plain sight within existing data, their strange multi-year light curves mistakenly filed as separate explosions. Our map of stellar deaths may be missing an entire category of slow, pulsating giants. Ultimately, the legacy of the zombie star is not a settled answer but a vibrant, open question. It embodies the dynamic and unfinished nature of cosmic science. Just when we think we have categorized the universe's most violent phenomena, the cosmos delivers an object that breaks the mold, shines in a way we did not predict, and forces us back to the drawing board. It is a reminder that our models are not truth, but our best current approximations, always subject to revision by the next strange glimmer in the dark. The search is now on for more of these undead stars, each one a potential key to understanding the ultimate limits of stellar life and the varied, spectacular ways it can end. The story of these 25 stars is not just a tale of cosmic oddities, but a testament to human ingenuity. How do we find a single, unpredictable needle in a galactic haystack of 100 billion stars? The answer lies in a technological revolution that has turned our entire sky into a laboratory. For centuries, astronomy relied on patient, individual observation. Today, it is a science of immense data driven by silent sentinels in space and algorithms on Earth. The first great leap came with missions like Kepler. For nearly a decade, this space telescope stared unblinking at a single patch of sky, monitoring the brightness of over 150,000 stars with exquisite precision. Its primary goal was to find planets by detecting the tiny, periodic dips they cause as they transit. But in doing so, it captured something else entirely, the unexpected. Kepler's continuous gaze revealed the bizarre, irregular dimming of Tabby's star and the chaotic dips of young Dipper stars like EPIC 204278916. It provided the long, unbroken light curves that let us see stars breathe, pulse, and erupt over years, not just nights. Kepler's successor, the Transiting Exoplanet Survey Satellite, or TESS, has taken up the torch with a wider view. TESS scans nearly the entire sky, sector by sector, searching for transits around the brightest stars, but its all-seeing eye also catches stellar flares, outbursts from distant cataclysmic variables, and the subtle flickers of pulsating giants. While TESS and Kepler measure brightness, the Gaia mission is building a three-dimensional map of our galaxy. By pinpointing the position, distance, and motion of over 1 billion stars with staggering accuracy, Gaia reveals the runaways. It is Gaia's data that lets us trace the paths of stars like Zeta Ophiuchi and Ae Aurigui back to their explosive or chaotic origins, confirming they are fugitives from other parts of the galaxy. These telescopes generate a flood of data so vast no single team of scientists could ever hope to examine it all by eye. This is where the second revolution happens, not in orbit but online. Platforms like Planet Hunters invite the public to become explorers. Volunteers from around the world examine light curves from Kepler and TESS, looking for the unusual dips and patterns that automated algorithms might miss. The human brain is exceptionally good at spotting anomalies, and it was citizen scientists who first flagged some of the most bizarre light curves for professional follow-up. They are a distributed neural network of curiosity, scanning the cosmos from their home computers. And finally, there is the silent partner in this hunt, artificial intelligence. Machine learning algorithms are now trained to sift through millions of light curves, learning the signatures of normal variable stars so they can flag the true outliers. They can detect the subtle pre-outburst brightening of a star like V838 Scorpii in archival data, or correlate faint multi-wavelength signals to identify objects like magnetars. This technological trinity, space telescopes for constant watch, citizen scientists for pattern recognition, and an eye for brute force data mining, has transformed our ability to find the unpredictable. We are no longer just looking at the sky, we are listening to a chorus of a billion stars, and we have built the tools to hear when one of them sings out of tune. This vast, interconnected system of discovery ensures that the next great cosmic anomaly, whether a zombie star or a silent giant hiding impossible elements, will not stay hidden for long. Our current tools have opened a new era of discovery, but the next generation of observatories will redefine the hunt entirely. The Vera C. Rubin Observatory, perched atop a Chilean mountain, represents a fundamental shift in scale. Its primary instrument is a camera the size of a small car, designed to capture the entire visible southern sky every few nights. For a decade, it will perform this monumental scan, creating an unprecedented motion picture of the cosmos. Where Kepler watched one patch of sky and TESS scans in sectors, Rubin will watch everything continuously. This means it will not just find the unpredictable stars we know about, it will discover entirely new classes of variability we have never seen. It will catch the faintest, quickest flashes, the slowest, most gradual brightenings, and the rarest, one-time-only eruptions that current surveys simply miss. Imagine having a security camera on every street corner of the galaxy, recording every flicker and flare. Rubin will provide that complete record, turning anomalies from rare curiosities into a rich catalogue of stellar behavior, allowing us to finally see the full spectrum of how stars misbehave. While Rubin paints the broad strokes of this dynamic sky, the James Webb Space Telescope peers into the finest details. Webb's infrared eyes are uniquely suited to solving the very mysteries we have explored. Take the case of the dusty Dipper stars or the self-eclipsing R Carinae Borealis. Webb can see directly through their obscuring veils of dust, analyzing the chemical composition of the material itself and the star hidden beneath. For Przybylski's star, with its impossible elements, Webb's exquisite spectrographs can search for fainter, even more exotic spectral lines, confirming or refuting the theories of neutron star pollution or unknown nuclear processes. It can dissect the complex nebulae around stars like R Aquarii or the homunculus of Eta Carinae, mapping their temperature, density, and chemistry in 3 dimensions to understand the precise forces that shape them. Webb turns points of mysterious light into detailed forensic reports, giving us the chemical and physical evidence to move from speculation to understanding. Together, these instruments form an unstoppable partnership. Rubin will be the alert system scanning the sky to shout, "Look over here, something strange is happening." It will find a star dimming in a bizarre way or a new point of light flaring where none existed before. Within hours, that coordinate can be handed to Webb and other observatories for immediate, deep follow-up. This rapid response capability is revolutionary. We will no longer study the aftermath of stellar eruptions from archival data, as we did with V838 Scorpii. We will witness them in real time, from the first flicker to the final fade, capturing the event's entire life cycle across every wavelength. This means the next zombie star, the next great dimming of Betelgeuse, or the next magnetar scream will be caught in the act, with all our most powerful tools already trained upon it. The ultimate promise of this new age is not just more data, but a deeper language. We are on the verge of moving from cataloging anomalies to understanding their underlying grammar. By seeing thousands of examples of every type of variable and eruptive star, we will begin to see the patterns within the chaos. We will learn which stellar tantrums are mere hiccups and which are death rattles. We may finally answer whether stars like Tabby's star are truly unique or just one extreme in a continuum of dusty systems. The mysteries presented in this video, the unexplained dimmings, the impossible elements, the repeated explosions, are not permanent puzzles. They are questions waiting for a telescope powerful enough and a survey vast enough to provide the context for an answer. The coming decade will transform these enigmatic points of light from characters in isolated stories into words in a grand, unified narrative of stellar life and death. The cosmos has shown us its most unpredictable faces, and now we are building the eyes to truly see them. 25 stars, each a universe of mystery in itself. From the self-destructing giants to the whispering corpses, from runaways fleeing ancient explosions to zombies that refuse to die, this journey has revealed a cosmos far from serene. The true lesson of these celestial anomalies is not that the universe is broken, but that it is endlessly creative. Their unpredictability is not a flaw in our understanding, but the very engine of discovery. Every strange dimming, every impossible element, every repeated pulse is a question written in starlight, challenging us to look deeper, think harder, and build better tools. We live in a galaxy that is alive with change, where the steady lights we navigate by are the exception, not the rule. This dynamic, often violent reality is not something to fear, but to marvel at. It means we are participants in an ongoing story, one where the next great revelation could come from any patch of darkness. So the next time you find yourself under a clear night sky, remember this. You are not looking at a static picture. You are gazing into a living, breathing, and spectacularly unpredictable arena. Every point of light has a story, and many of them are tales we have only just begun to read. Keep wondering, keep looking up, and join us as we continue to explore the greatest mysteries the cosmos has to offer.